All right, everybody, I think we can get started. Miranda, can you wave if you can hear us? Yay. Okay, she's got it. All right. Our next speaker is going to be a Zoom talk. We're happy to have Miranda Cheng from Amsterdam talking to us about normalizing flows and lattice field theories. And Miranda, we'll try and run the microphone around to ask questions and things. If you can't hear anybody's question, just let us know and we'll repeat it, okay?
All right.
Thank you very much.
Okay, so can you guys hear me? All right, so I assume that answer is yes, although I didn't hear anything.
Yes.
Okay, so I'll start by thanking the organizers for the invitation to give a Zoom lecture here. And so the title of my lecture is Normalizing Flows and Lattice Field Theories. So just a little advertisement. In 2 weeks or so, I'm going to give an extended version of this lecture in the IFI summer school. So just in case that you'd like to know more, then soon there will be more material available. Okay, so this is the condensed version. So now I'm going to try to, yeah, it works. Okay, so the outline of my talk will be, first of all, I'll give a little reminder of how sampling is done in lattice field theories. And in the second part, I'll introduce what's called the normalizing flows, which are special cases of generative models in ML. And in the third part, I'll see how I will show you how normalizing flows can be applied to lattice field theories and what the results are so far. So the first part, so we will start with what lattice field theories are. Well, we all know that lattice field theory can be thought of as the lattice version of quantum field theory. That's one way to think about it. And that's also the point of view we'll mostly take today. And so we just consider that we're discretizing space and Euclidean time in this part of the lecture. Okay, and it's, of course, also a useful tool in condensed metaphysics. And moreover, it's the main computational tool in the quantitative sense for performing non-perturbative QFT calculations, such as, for instance, QCD. So why do we need to still care about it? Well, because we really need faster and more accurate lattice field theory calculations for many different types of physical systems. And for the HEP audience, well, like one big very good example is the muon magnetic anomaly that has not been completely settled because of there's possible discrepancies. And then in order to settle that, I mean, we would like to have a high enough accuracy lattice field theory, lattice QCD computations, but that is sort of quite a lot beyond reach right now due to computational constraints. So clearly, we would like to improve our computational handle on lattice field theories in general, and also from the computation or from the machine learning perspective, right? For instance, lattice QCD is one of the longest standing computational challenges, but at the same time, we know the physics really well, right? It's not just some random problem that's, you know, you have nothing to compare to. So it's a great testing place for new ideas and new methods, new hardware in computing. Okay, so just very quickly, how do you write down a lattice action? Okay, so we think about discretizing space-time as these lattice points that I drew to the left, to the right, sorry. And I'll work with a finite lattice with size L in each dimension, and the total dimension will be D. And for instance, let's take a single scalar field as an example, right? What you do is you replace derivative with like its discrete version as usual, and then you replace a field, the scalar field, for instance, to some L to the D collection of single value functions, right? And then in this way, you get a lattice action from the QFT action. And why this is interesting, of course, is because now the infinite dimensional, notoriously difficult infinite dimensional path integral is now becoming a sum, a finite dimensional integral, which you in practice approximates by averaging over samples. Okay, so what do we mean by samples? So samples are examples of field configurations. And moreover, you want to draw your sample from the physical distribution. Here it will be just given by in Euclidean spacetime, like by the given by the Boltzmann weight. So this is the distribution we would like to draw our samples from. However, if you have an interacting theory, this distribution will not be too simple and will be hard to sample in general. So what do people do? Well, people do Monte Carlo, Markov chain Monte Carlo, right? So you build a Markov chain, and then to construct the chain, what you do is to generate a proposed sample, usually with like some, local update from the previous sample, okay? And so that's how you go to find the I minus one to the find I to the ith configuration. And but in order to to guarantee that you're sampling with respect to the distribution, you add an accept or reject step. Okay, so that's called the metropolis algorithm. We'll say much more about it later. And so what's the problem? The problem is goes on the name of critical slowing down. So it refers to, the fact that we have typically very slow exploration of the large configuration space, especially when your system is large. We will talk about what large is shortly. Okay, and this is manifestly bad when you're using local updates. For instance, in the spin system, right? You flip one neighboring spin each time, and then you reject or accept. Then in such a way, it's like it takes forever to go from an all spin up configuration to an all spin down configuration. So this is basically the essence of critical slowing down. And in practice, this problem poses great computational challenges and causes bottlenecks. Okay, so when is this an especially bad problem? Unfortunately, these aren't exactly the regimes we care about. Okay, so the name critical slowing down, as the name suggests, it's especially bad near the critical point, because when you have a phase transition, then when you're near the phase transition point, then what happens is that your correlation length becomes very, very large. So there's very long range correlation in so measured in terms of like lattice spacing. So this makes the effective volume becomes very, very large. Or if you are approximating some QFT, then you want to, of course, take the continuous limit by letting the lattice spacing to become smaller and smaller. So that will require, for a finite physical size system, the number of lattice points to be larger and larger. Okay, so the dimension of your problem becomes really large at a certain point. So that's the challenges. So what do we do? Well, people have come up with all kinds of ways to mitigate the problem, and many times it's like cater for a specific theory, such as the Wolf algorithm, or another way is the hybrid Monte Carlo, but we won't have time to go through that today. And I would like to just point out that there's a very nice theoretical solution that goes under the name trivializing flows that's proposed by Lösche in like 15 years ago. So the proposal is that it would be really nice if we can find an invertible map F such that the F inverse actually undoes all the interactions, all these annoying things that make life hard, right, for you. But this is a bijection. So what you can do if you have such a map is that you could sample here, you know, according to the distribution with all the complicated interactions being undone. So it's a very simple distribution, for instance, Gaussian. Okay, you can sample here, and then you push the sample using this map, and then it becomes, you know, your desired samples. Okay, so that's the essence of the trivializing flow, because it trivializes the interactions. So that's a beautiful idea. And in some cases, it can be achieved, but in general, not. So the question is then how to find such a map. Okay. So that finishes the first part of my talk. So I'm going to the second part. So I'm going to introduce, to switch gear and talk about normalizing flows. Okay. So as I mentioned, these are special classes of generative models, we all heard about generative models. So you have a architecture, and then you train so that this architecture now acquires some fixed parameters. So this becomes your generative models. You can use this trained model to generate all kinds of contents from music, photos, you know, drawings, or field configurations. Okay, so how do normalizing flows achieve this? So the idea is indeed to find a map F that from what we call the latent space in that jargon to the configuration space. So which maps a simple distribution to a complicated one. So especially we know, you know, what the push forward with respect to this map is. Okay, the distribution is pushed forward such that it's just, you know, the original distribution and corrected by the volume factor that we know is given by the determinant of the Jacobian of the map. Okay, so oh yeah, here maybe I didn't yeah, so yeah, that's right. Okay, so that's the idea. So how do we want to build such good maps? What do we mean by good normalizing flows? Okay, to achieve what we wanted to achieve, right? We have the following keys we need to achieve to have good feasibility and efficiency. First of all, the prior should be easy to sample, otherwise it's useless. It defies the purpose. So for instance, a lot of times it will be Gaussian, so hence the name normalizing flows if you want. And the second is about the architecture. We want this map, as I mentioned, to be invertible because, you know, we need both sides in order to sample. And then we want it to be expressive. And we also wanted to have tractable Jacobian so we can reliably compute this push forward distribution. And then, of course, the final result we want is high accuracy in terms of how well the push forward distribution approximates the target distribution. Okay, so now I'm going to talk about different elements of these requirements. So, by the way, if there's any question, please shout. And I might not see the chat, but I think someone can relay the questions. Right. So let's go to the architecture part because the prior part is obvious. Let's say we choose it to be Gaussian, although there's also art in what good priors are for what problems. So architecture, as I said, we have these requirements for the map F. And to achieve this, oftentimes people use a sequence of maps. Okay, obviously that increases your expressiveness, right? So I think the diagram illustrates the idea very well. So I'm not going to say more about what I mean by a sequence of maps. So in particular, the determinant will be the product of the determinant. So one specific architecture which goes under the name coupling flows does this smart thing. So it partitions, interesting. It's a kind of not the right, anyways, the right slide, but anyways, it's close enough. So I can still talk. So it partitioned, right, the space of the space of where data lives into, you know, two parts. It doesn't have to be equal size. So we partition it into XA and XB, and then also the YA and YB correspondingly. Okay, so then we use this map in this form. So X remains the same. Okay, so the B part remains the same. Then the A part transforms depending on itself and also the B part. Okay, so what you get is a triangular form of the Jacobian. So, well, that's sweet, right? Because the map is invertible if this map H is invertible. And then you can compute the Jacobian of this whole map F if you can compute the Jacobian of H, since the two are equal due to the triangular form of the Jacobian. So that's the smart design of coupling flows. So one specific class of coupling flow goes under the name real MVP, the real value to non-volume preserving flow. So the key feature is that it separates, you know, the data space into two parts in this checkerboard pattern. So the first time, say the white part, that's the white, sorry, I mean red. The red part is fixed and the blue part transforms. And in the next step, it gets reverted and so on and so forth. Okay, so you always have tractable Jacobian. But you can, of course, notice that the partitioning breaks the part of the translational symmetry. Okay, so that's one class, the coupling flows. Another class is, well, it takes a different idea. So you could stack, you know, many, you know, maps together. So let's take then the continuous limit. Then basically it becomes an ordinary differential equation. So this goes under the name of neural DEs. Okay, for obvious reasons. So you just choose a time, big T, as, you know, your integration time, right? And then you learn this ODE. In particular, you learn this vector V of theta, such that when integrated, okay, between time 0 and time big T, you get a map, right? And this map will be your normalizing flow. Okay, so you can, sometimes people say that it's a single layer structure because there's one OD. Sometimes people say that there's infinitely many layer because it's continuous, but you get the idea. Okay, so it has many advantages in terms of flexibility and expressiveness and well, basically because almost by definition, well, in particular, if V is Lipschitz, then you're guaranteed to have an invertible function after integrating a neural ODE. And it's tractable when you choose, when V is chosen smartly. Okay. And there's other advantages and so on, but I'm not going into that today because I have no time. So then let's go to the third part of what we want our normalizing flow to do. Namely, we want the push forward distribution to be a very good approximation to the target distribution, right? So how do we ensure that this happens? Well, the answer is clearly training. We have to train our parameters. In the coupling flow, we train that map F, H, and in the ODE, we just train the ODE. Okay, so how do we do that? We choose an ansatz, parametrizing, you know, the flow in some way, and then we minimize the loss function as usual. So the loss function should measure somehow the difference between the proposed and the target distribution. So KL divergence is a familiar choice, but today we will use the reverse KL divergence. So we put, because remember, KL divergence is not a distance and it's not symmetric in particular. So we will put the proposed distribution in front. Okay, so the reason for doing that is because if you do that, right, and write down the definition, then you can use the so-called reparameterization trick, namely because you want to draw samples when computing the KL from the proposed distribution. We know that it's the same as, you know, the pushback of the samples in the original distribution. So sorry, this is not rho, this is the prior distribution, the Q0 that I wrote down before. So, okay, we can just sample using the Gaussian distribution. So in particular, so that's an easy computation, this KL divergence, as long as you know you have a closed form for the target distribution, which is something we don't have in image applications, but we do have in lattice field theory computations because it's just given by the action. Okay, so and in particular, if you're wondering about partition function, it all drops out. Okay, so that's handy. So in particular, it does not need samples to train. Okay, otherwise it defies the purpose because we need the flow because samples are hard to come by. Okay, so then after training, supposedly we have a model that generates the proposal distribution. We still need the Metropolis Hastings step to correct for the remaining discrepancy. Okay, and this step just is, as I mentioned, an accept reject step, and then basically you accept the proposal with this probability that's given by the mean here. In particular, if your distribution fits nicely, perfectly with the target distribution, then you always accept what you propose as, you know, expected, right? So theoretically, it gives you a asymptotic convergence. Right, so here's some summary of what we do, right? We parameterize the flow, we draw samples from the easy distribution, from the normal distribution, we compute the reverse KL, and then we do an optimization step and update. And then if the efficiency is still not to your, you know, to your liking, to your satisfaction, then we do it again. It's just the training process until at a certain point you stop the training and say this is a good enough flow, and then you use it to generate proposal samples. Okay, and then you either, you know, accept or reject and build your Markov chain, and then with these samples you can start computing things, or, you know, generate your fake pictures, no matter what you want to do with it. Okay, so how do we then evaluate if a network is good enough or not? Oh, so clearly, right, for efficient sampling, we want the acceptance rate to be high. So acceptance rate itself is already just a very good evaluation. Or to make contact with, for instance, the literature of lattice field theory, people talk about effective sample size, people talk about the autocorrelation time, so which are given in terms of, you know, again, these quantities. Okay, here I didn't give you the definition of gamma, but gamma is the autocorrelation functions measuring how correlated different configurations in the Markov chain is, right? You want this number to be as small as possible. Okay, at least you want it to drop as quickly as possible when the distance between two configurations in the chain gets larger and larger. Okay, but I need to remark here, since in this flow-based sampling, right, we draw samples independent of the previous sample. So this is called the independent sampling. Unlike let's say the usual Ising spin on MCMC, where you're just flipping some spins from the previous configuration. So in case of this independent sampling, basically all the three measures of performance have just the same, exactly the same information, because the only source of autocorrelation in the chain is by rejection. Okay, because you repeat the sample if a proposal sample is rejected, and hence the correlation. Okay, so that's just the sort of the workflow of normalizing flows in when applied to sampling. So now an obvious question is, can we use normalizing flows that's from the ML literature to implement or to find the trivializing flows that these lattice physicists talk about? Okay, so that's the subject of the next part of the talk. So how do we apply normalizing flows to lattice field theories? Any question?
You had this example with the with generating images. Can you explain what the latent space and the configuration space is in that situation?
Well, for instance, if you're talking about the latent space, for instance, if you, let's say, be very concrete, you have grayscale picture, so there's only one channel, like with n pixels. Okay, so here we always take the latent space to be the same as configuration space, so r to the n. Okay, so then you want to, for instance, put independent Gaussian distribution, so every pixel can be sampled independently on this on the latent space, and then you want to find the map such that in the configuration space, this Gaussian becomes, let's say, the distribution of natural images. So that's what you want. Does that answer your question?
Yeah, thank you.
Yes. Yeah, so in that situation, you don't want to use the reverse KL. You want to use the forward KL, because you do have samples. Yeah. Okay. So right. So there's no more question then, or okay, good. So I continue. So now our application is the physics computing application, let's say. So where the target distribution is a physical Boltzmann distribution given by some lattice action. That's not easy to sample. Okay, so first we'll talk about how we estimate the computational cost, and especially its scaling behavior in the setup. And second, we talk about some nice aspects of machine learning that one should make use of. And then, okay, this is a mistake, because I'm not going to talk about, well, okay, yes, I will talk about it. In the third part, I'm going to introduce a very specific architecture. Basically, it's the architecture we use in our work, in our own work. Equivariant continuous flows, we'll explain what it is, and then we will describe for you the results of experiments so far. Okay. So I should start with introducing some very interesting and pioneering work on applying the flow ideas to lattice field theory. So there are many papers. The first one of them starts in 2019. So they apply the normalizing flow that's given by the real MVP flow to the problem of 2D Euclidean 5 to the 4th theory. Okay, and there are some generalizations, many generalizations after that. But I won't have time to go into that. So now let's start with thinking about computational cost, because that's the issue we would like to address from the very beginning. So in this flow-based approach, right, the computational costs include the training costs and the sampling costs, right? And then the training cost in particular has no counterpart in traditional MC methods. So the way we evaluate computational costs should also be somewhat different. And the sampling costs, of course, the sampling cost goes down if your flow is very well trained. So the acceptance rate is very, very high, right? Because you don't need to throw away many generated proposals. So there's a bit of trade-off between the first kind of cost and the second kind of cost. So that makes the discussion about the computational cost very involved, and it's a topic I'm not going into today. But let's just focus on the first part. Okay, because what's observed, since the flow-based model has also this additional training cost, so we, apart from looking at the sampling cost, we should study the scaling behavior of the training cost. So that's done by Debio et al. They analyze these real MVP-based models, and then they the alarming news is that although the sampling cost might seem to be, promising, but the training cost seem to have like very steep, more than exponential growth together with. So the training cost as measured from the number of samples that you need in order to achieve a certain, here they use the autocorrelation time as a measure of accuracy, goes up, right? So it's a log plot, right? So you see that it's exponential, and L is in this case, the square root of the number of lattice points. Okay, so now the question is then, how do you make it work for larger lattices in this case? Because here okay, I'll show you the numbers later. So, but first, maybe just on this slide, just the idea of, what the challenge is. Okay, and the second part is these costs. Well, as I mentioned, as I stressed, they depend on non-trivial interplays between different factors, between the training cost, the sampling cost, and how hard the physical theory is, and what the model architecture should be, and how we choose the model hyperparameters, and so on. So these all can affect greatly how the costs look like. But before going to these specifics, we can ask, a question. So is there any intrinsic properties of machine learning methods that we could exploit when comparing to the traditional MCMC methods? And this is the part I would like to stress. So, because the answer is yes, because we're learning something. We're not just repeatedly doing the sampling calculation. The idea is that our model, through training, actually learns something about the physical system. So how do we exploit it? Well, so to think about it this way, right? And then how do we know that, for instance, a physical theory is defined by its coupling constant, and then in some regions in this moduli space, the theories are harder to sample. In some regions are easier to sample, for instance, depending on your correlation length and the size of the interaction and so on and so forth. But we also know that there is certain locality in most part, right? I'm not sure about across the critical line a priori. I'll show you the plots later on that. On that, but I mean, away from drastic changes, right? Then you expect the physics to be very similar. So unlike in the traditional MCMC methods, if you change your coupling constant a little bit, you need to, restart again your MCMC procedure, including the burn-in and so on and so forth. But we think like our model can, if we can learn one theory, we can also know something about the neighboring theory, right? So, and another way is that we're changing the UV cutoff when we change the lattice size in some sense, right? Because we're changing the cutoff scale. Okay, then that we also know is given by the RG flow, and the behavior should be continuous. So if you know something about one lattice size, you should also know something about other lattice sizes. So how do we in practice exploit this learning effects? Well, in the first instance, when we change our coupling constant, what we will show you is that it is possible to learn a theory conditional flow. Namely, we learn a flow that is continuous in the space of couplings. Okay, so you train it once and then you can sample for a big area in the modular space. That's clearly something desirable compared to usual MCMC methods. And then the other way, in other aspect, is that when we are changing the lattice sizes, then we could just transform the weight, right? So you don't initialize your network for a larger lattice via random or uniform distribution, something that's clearly uninformed. Instead, we use the weights learned for smaller lattices and transform it, right, in a reasonable way to a larger lattice, and that could save a lot of time in training. So these are the ideas that we should use in order to beat this exponential growth of either the sampling cost or the training cost. Okay, so now I will try to wrap up in the last 20 minutes or 25 minutes, but giving you concrete examples of how these things can be put into practice. So the third part of my talk is to introduce a specific architecture that we call the equivariant continuous flow. So as the name suggests, it is an ODE flow, the neural ODE that I told you about. We choose it because of its many, many advantages that I didn't have time to tell you about. But eventually we choose it because it works well. Right, so to remind you of the setup, right? So now we have a field configuration that's basically L to the D number of scalar functions. So we associate a number, for instance, in the scalar theory example, we associate a number to each lattice point. Okay, so that is what we call a point in the configuration space. So the latent space is the same, right? So we put some prior distribution there. So in the work so far, we use independent Gaussian, but it's a different story that I won't have time to tell you about. But there's some much smarter prior to choose. But let me not talk about that for now. So some prior distribution, some form of Gaussian. And then we want to learn the flow by learning this theta parametrizing our ODE flow. So how do we parameterize this vector V of theta? We don't just want to, just mindlessly throw a neural network at it, because there are some other properties we would like to have. Okay, so this property goes under the name equivariant. So in view of time, I'm not going to give you a whole introduction of what equivariance means and how it's achieved in the context of neural network, but let me just illustrate it for very simple example. So namely the same example, two-dimensional 5 to the 4 theory. So what I'm going to tell you is from now on, it's based on these two papers with my wonderful collaborators. So so the parameters, basically the only three parameters here is this lambda, okay, the strength of the 5 to the 4th coupling. And the symmetries in this theory has two parts. The first part is the global symmetry of the quantum field theory, namely phi to minus phi. And then the other part is the space-time symmetry, namely the 90-degree rotation and the shift symmetry, okay? So we want, as I mentioned, a theory conditional neural ODE flow. And let me remind you, theory conditional meaning that we want to have a family of flows. So one flow for each choice of a theory that's specified by the 5 to the 4th coupling lambda. So that's how we want to set up the problem. So we want to set up problem ambitiously. We don't just want to sample one theory. We want to sample a series, a family of theories. Okay, so how do we parameterize it? As I said, we don't just throw a random neural network at it. We parameterize it in some simple way. So so this weight in bold W is what we would like to learn. So these are coefficients of what? Of this time kernel K of T. So different D, different index D, right? So indicates a different Fourier time kernel. Okay, so basically you would want your vector field to be able to depend on time, because that increases the expressivity, of course. So in other words, if you think about this, you know, OD as some trajectory, you would like to have the freedom to insert force in this process, in this ODE process. Okay, and H, what is H? H is some feature built out of the field value at site Y. Okay, so X and Y, they denote different lattice points. So F denotes different features. So W, this we want to learn, then depends on the point. Well, the lattice side you're flowing and the lattice side you're looking at, right? So interaction, in other words. So D is the time kernel and F is which feature that's built from the field value at lattice side Y. And moreover, you want it to be, you want this learnable parameter to depend on the strength of your 5 to the 4th coupling. So we do this in this way. So J of lambda is again some basis expansion function, okay, that interpolates in different ways between small lambda and large lambda and so on. So that's the answer. So what does it have to do with symmetry? Okay. So, oh yeah, so before I go to the symmetry, so there, of course, hyperparameters are just how many time kernels, how many, you know, features, and so on and so forth that you choose. So the symmetries, well, you will want the symmetries to be preserved. So for instance, let's take a look at the space-time symmetry that transform the lattice sides denoted by X and Y, right? So, so we want it to be invariant. So the weight is invariant when you just transform the points, you know, simultaneously with a group action, no matter whether it's rotation or no matter it's reflection. So this is analogous to the idea of convolutional neural network, also has this kind of space-time, discrete space-time symmetry, okay, in the same way. And the second is global symmetry. So we want to choose our feature such that if you flip the sign of phi, then you flip the sign of its feature, right? Because remember, right, the left-hand side is phi dot, right, which obviously also flips the sign. So you want it to be, the ODE to be consistent with the symmetry. So that's why we choose the feature to be given by the sine function with learnable frequencies and without the cosine function, because that would break the symmetry. Okay, so if all this is preserved, then the ODE preserves the Z2 symmetry. So if the prior distribution has this flip sign symmetry, then the resulting distribution also has the desired flip sign symmetry that we want. So in the broken phase, we're not going to get stuck. Okay, so more generally, what you want is this general equivariance condition. Okay, so I think it's quite, this blue equation is quite clear what it means. It just shows you, it just tells you that the ODE is compatible with the symmetry. Okay, so what do we want to do with it? Well, we then throw this network at different lattice sizes. So the highest we could go is 64 times 64, for which we still get very high acceptance rates, okay, 60, 70%. And then we check our the performance of the flow by comparing physical quantities, including the correlation length and the chi2, the susceptibility, okay, against results we obtain from just running the Monte Carlo. Okay, so that's one sanity check. And then another interesting experiments is the ablation study, because well, the equivariance is or not, whether you want to bake the symmetries in or not, is sometimes, you know, depending on the taste. Because another attitude is just don't give any prior knowledge, just throw the network at it. If the network is strong enough, it learns the symmetries anyways. Even if you include the cosines, the network should learn how to, you know, to put the coefficient to 0. But sometimes it doesn't. I mean, for aspects as fundamental in physics as symmetries, the result is that, yeah, it's much better to bake it in. So with the ablation study on the left panel, right, we so this is just testing the space-time symmetry for now. We could have the same exactly the same network structure architecture. We just take out the symmetry. And you see the orange line performs consistently worse than the blue line. Okay, and the right panel is the comparison with real MVP, which I might remind you that breaks part of the shift symmetry. You might think it doesn't matter, but you see the zagging after like training to death, basically trained till saturation, is still doesn't learn the symmetry perfectly. Learning the symmetry perfectly, meaning that all 4 lines are just straight, okay, because they're related by shift symmetries. Okay, so that's things to say about symmetry. And the other aspect of symmetry is global symmetry. So in this 5 to the 4th story, it also has a very clear advantage compared to the real MVP model that has no manifest symmetry, because they do have encounter difficulties when sampling in the broken phase, just the usual story, you get stuck. But here, the problem is non-existent, because as I told you earlier, the push-forward distribution, because of the equivariance, is manifestly symmetric. Okay, so that's about symmetries, but what's really interesting is are two things, I think. One is just the absolute accuracy. So the right take are the real MVP results. And then the main panel is the equivariance continuous flow results. So for instance, their largest lattice size is 32 with ESS basically below 5%. And then our highest result is above 90% for that lattice size. So that's the sort of absolute accuracy. So it also shows you, I think, the interesting lesson is that by choosing the different architecture, you really get really different results, although both are normalizing flows. So details really matter in applications. Okay, and these are really big details. These are not really even small details, because this is an architecture choice, what I'm talking about. And then also, what's the interesting is if you look at the dashed line. Okay, the dashed line denotes the result obtained by using the transfer learning. So you don't start training from scratch. You start training using the smaller, using the parameters, using the weights from the smaller lattice as the starting point. Okay, so for instance, this might seem like the difference in time is not too drastic, but actually it's a factor of 2 because this is a log plot. So we expect, like, if you really want to go to, you know, lattice QCD, for instance, 4 dimensions of, like, you know, each with L equals 200, let's say you really need this transfer techniques in order to get there. Okay, so the second plot is on scalability. So the scalability is that, let me be quick in view of time, both in terms of the absolute number of the training samples. So you could compare the, you know, here we're talking about, like L equals 64 for 10 to the, well, okay, you can read yourself. I don't need to read the legends. But more interesting is that this is a sort of a this indicates, we don't have a proof, that this indicates a much milder scaling in terms of training costs. Okay. And we have some intuition why this is the case. This just given by the, you know, by how newer ODEs can be trained efficiently, but we don't have like a really solid, rigorous mathematical analysis of the scaling behavior, which would be desirable. Okay. Okay, so this, yeah, so I showed you the transfer learning works, and now I should show you also something that I find very pleasing, namely the theory conditional flow works. So let me remind you that we train once and for all for a big range of the coupling constants. So so we have a sampler for each of the 5 to the 4th coupling strengths lying in that regime. So what's maybe wasn't clear to me before we did the experiments is that you could do that extending through both sides of the phase transition with no problem. So this is demonstrated by this plot of the susceptibility plot. It lies perfectly on top of each other, also together with the the theoretical results, and using just one flow. Okay, so that works really well. So that's all I want to say about the experimentations we have performed so far. So to conclude, in general, so the big picture, conclusion is that I hope I have persuaded you that flow-based models have potentials in lattice field theory studies. Although now we're not beating the supercomputer results in LQCD yet, but it has potentials. And before we can go there, I think it's worthwhile to understand the scaling behavior of these new type of sampling techniques that uses machine learning. Okay, so smaller lessons learned from the experiments is symmetries do help in physical systems, at least in this case. And also it's sometimes just a little bit of thinking with no complication to implement equivariance. So I would like to advocate that if you have symmetry, just try to bake it into your network. And the second thing is continuous flows have the potential to be very suitable for this kind of applications, and with just one single layer continuous flow. And this is also very successfully applied, and actually we drew our inspiration from this work from the application to multi-body systems. Okay, and the third lesson is it's viable, it's theoretically appealing, and also corroborated from our experiment that we should really leverage the power of learning using transfer learning and related techniques. And of course, there's a lot still humans would like to do, would like to see, namely more experiments on all kinds of lattice field theories, including the gauge fields, including the fermions, including all these things that are really interesting. And there have been many works on this, but due to time, I won't have time to tell you about this. And then also there are other ways that flow-based models and in general machine learning models can help lattice field theory, not just the direct application I talked about. For instance, you could use the flow-based model to try to incorporate that with the traditional Hamiltonian Monte Carlo methods. There's all kinds of ways. And then we need to keep improving on the performances for larger lattices, for sure. I don't think it's now the time to just throw our network to a supercomputer and just try to beat it. I think we need, more engineering thoughts before we do that. And in particular, we'd like to have more understanding of the scaling behavior of the training cost and sampling cost, and how the attainable accuracy, how it plateaus, how the accuracies plateaus, and so on. Okay, so moreover, a more systematic study of the model quality is desired, because all these measures like ESS, namely effective sample size, acceptance rates, and autocorrelation functions, they're good, but they can miss things, okay? That's, they can miss inaccuracies of model qualities, okay? So we also need to think more systematically and honestly about that. And then moreover, there are many, many other physical applications. Okay, so that's the end of my talk. I hope you are entertained somehow, and please ask questions if you have any.
Yeah, hi. Yeah, great talk. I was interested in the part where you talked about the RG group. So you say that
talk about what? Sorry, I didn't catch
the part where you talked about the RG group.
The RG group.
Yeah. So
did I talk about RG group?
Sort of, I think.
Okay.
So
all right. Okay.
I think
I did mention because the UV cutoff connection.
Yeah,
Yes.
I think there was a slide where you parameterized the normalizing flow by the coupling constant. Right?
Yeah.
And does that mean you can sample like field configurations from different points in theory space accurately?
Yeah. So that's what I try to convince you of using this plot. Yeah.
Okay.
So
sorry.
Yeah. So the horizontal axis is the coupling constant lambda. Yeah.
Do you think that this could be used to like identify fixed points in RG
Yeah,
space?
absolutely. Yeah, yeah. Of course, in this theory 5 to the 4th, we know numerically where the phase transition point occurs, and we also know like what these exponents, right, gamma and nu's are. They're given by basically the azimuth. But I mean, in generically, there's at least one of these things you don't know, but you could just fit it. You could just or you know, we could hand you samples, and then you could do all the analysis and extract all these very interesting physical properties. The key thing is just where does phase transition happen in your system, for instance.
Do you know of any work that's applied this to like 2D CFTs where these like exactly solvable systems?
That's a very interesting thought, but I don't know, because I think I'm not aware of other work doing this theory conditional thing in the flow-based sampling setup in the lattice field theory setup. So I think, yeah, so this is just what we come up with. And so far, I haven't seen people using this to compare with like 2D CFD stuff and so on.
Okay, thank you.
So that's interesting.
Other questions?
Wondering, do you need different architectures for different actions?
Yeah. Yeah. So if you have, well, it depends, right? I mean, for instance, the architecture, I would just say, is a NeuralD. But for instance, the dimensions changes if you have 2 scalars instead of 1. The dimension changes, or the parametry how we choose our features will change if you're, let's say you have, right, these are the features we choose to fit the Z2 symmetry, right? Because we have Z2 symmetry. But if you have a complex scalar, let's say 2 scalars, then you have rotation symmetries, then I will give you some features that's compatible with the U1 symmetry. But these are, yeah, but I would think like this basic equation won't change. It's just how you parameterize things, how you choose your feature, and so on and so forth. So for instance, we're working on applying this to gauge theories. So things become more interesting and complicated because you also have gauge symmetries, not just global symmetries. So then how we parameterize these features will be different. But the formula looks the same.
Have you thought about string field theory? Doing this
Someone asked me this before, but the short answer is no. But if you have ideas, I'll be very happy to discuss. Because
I actually have one. So thank you very much for the talk. I just want to go back to the theory with the lambda bit. So you had a formula up with how you've separated the lambda variables with the parameters you're training in. So I was just wondering,
you mean this
why
slide?
is that?
You want the
I think
slide
it was
or
earlier when you talked about a symbol theory, you had this formula up with a v theta equal to an expansion of stuff, and then there's an w. Yep, that one. So
yeah.
I was just wondering. So it seems like you're saying that The J lambda are some sort of like a basis. I was wondering, is that like a complete basis? Is that a general thing that you can write it down? Because it seems like what you're claiming here is it's theory conditional only because you can write it in this form and you can separately train the parameters without putting the couplings in. But I'm not sure if I am intuitive why it decouples, if that makes sense.
Well, we know that this coefficient W of the left-hand side should be a function of lambda. So then what remains is how you parameterize this lambda dependence. And I'm not sure I fully understand how to answer your question.
I guess like if you're expanding in terms of basis expansion function, then you have to terminate your result at some point, as in some bases.
Yeah.
And
so
that incurs error,
number.
doesn't it? Because your J lambda is not complete. So your flow will not be exactly lambda dependent, independent, if that makes sense.
Yeah, I understand. Okay, I think I understand what you mean, right? Because suppose you have some complete basis, but then you need of continue, because these are continuous functions of lambda. So you need the complete basis, and then you need infinitely many of them. You choose some your favorite orthonormal basis or whatever, but there's infinitely many of them. But we need to choose the truncation smartly, right, in neural networks, right? Because we don't have infinitely many channels, so we need the smart truncation. So of course, once you truncate, it's no longer a complete basis. So yes, so then at that point, right, like choosing which basis really matters. And then here you see that what we're doing is we sort of triple the space, or cube the space is a better word, right? We take 3 of these truncated of the complete basis, right? And then we put 3 trainable parameters in, right? One takes care of the time kernel coupling, how if you want how time kernel aspects coupling to the lambda. One takes care of the feature, and the other one takes care of the spatial interactions. But they all depend on, we let them all depend on lambda separately. But strictly speaking, if J lambda of infinitely many of them gives you a complete basis, you shouldn't need this, right? You just have one coefficient and then just train that coefficient. It should be mathematically equivalent, but sure, because we're truncating, right? And training dynamics is not always easy. So how you parameterize things in this way does matter, right? So we try a few versions and this works the best, and it's not expensive. So that's an engineering choice in the end that you're making.
Thank you.
All right.
I mean, of course, there are mathematicians who can analyze these things rigorously, right? I mean, what's the truncation error and so on. And separately, the training dynamics, that's another big piece of mathematics that you could try to tackle rigorously. But in practice, I don't do it. I just some reasonable choices and try it and choose the best.
All right. Thank you very much, Miranda. That was an excellent talk. I think we need to break here for lunch, but let's thank her again. And
Thank you.